Okay, now we want to now study the simplification of block diagrams when we have multiple inputs and multiple outputs. Previously, we studied how to simplify a block diagram if you have a single input and a single output. Look at this example. We have R1 and R2. These are two different inputs to my block diagram, and then I have Y1 and Y2 that are two outputs of the system. So if I'm being asked to simplify this block diagram and find a single transfer function that represents the system, what should I do? Well, the answer is that doesn't make any sense. You find the transfer function. Think about it. What's transfer function? Transfer function is the ratio of output to input, right? So the ratio of the Laplace transform of the output to the Laplace transform of the input. If I don't know what's the input and what's the output, that question doesn't make any sense. So if somebody says that to me, somebody asks me, what is the transfer function in this case? I have to ask them, what do you mean by that? What do you mean by transfer function? Transfer function from which input to which output? Then if they say, well, from R1 to Y1, I simply, to find transfer function between R1 and Y1, assume that Y2 doesn't exist and R2 doesn't exist. If I'm being asked what's the transfer function between R1 and Y2, again, I assume R2 doesn't exist and then Y1 doesn't exist. So, see, this is the general multi-input, multi-output block diagram. Then if I'm being asked what's the transfer function between Y1 and R1, I just remove everything else, all other inputs and outputs, to be able to simplify this block diagram. And this is the case when R1 is the input and Y2 is the output. Okay, so we studied how to simplify block diagrams. Now we want to find the relationship between block diagrams and ordinary differential equations. Remember, if you had ODEs and we wanted to write or to find the same system's representation as a transfer function, we would take Laplace transform. That was our tool to get from one way to represent our system to a second way to represent our system, which was transfer function. Now, if I want to get block diagrams and I have differential equations, what would I do? Well, notice that block diagrams are drawn for transfer functions. So if I'm being asked to plot the block diagram for a differential equation, some people might think, well, that simply means I need to take the Laplace transform, write transfer function, and then just put that transfer function in a block. But that's not what we mean when we say plot the block diagram for a differential equation. What we mean is that we are asking you to plot the block diagram for pieces, for constructing pieces of a system. So before we do that, before we start plotting a block diagram for differential equations, let's first think about the definition, right? And remember that we studied in the Laplace transform section that integral is equivalent to 1 over s in the Laplace domain, and derivation is equivalent with just an s. So if I have a signal y and I have it shown on the page, and if I have y dot here, what would be inside this block to make sense? What is the action that can convert y dot to y? Well, I need to take the integral of y dot to get to y. So inside this block, I should either put an integral sign or in the plus domain, I just put a 1 over s. So with this trick, I can create from y of t, y dot, and then y double dot, and then y triple dot. So if I have a signal, if I say, okay, you know what, I call this point here on my page y, I can, with putting 1 over s blocks, create higher order derivations of that signal, and that is what we use to draw a block diagram of a differential equation. Okay, so let's start drawing block diagram for differential equations. We are going to study two cases. In case 1, we don't have derivatives of the input. In case 2, we have derivatives of the input. So our equation has y dot, y double dot, and higher order derivatives of the input. So case 1, we don't have derivatives of the input. So we have a differential equation here. We have, like, assumed like a2, a1, a0, and b0 are numbers. Assume it's like 5 y double dot negative 1 y dot plus 3y equals to 17u. Okay, there is no u dot anywhere. That's what we mean. In case 1, we don't have derivatives of the input. There's no u dot. We just have u. So if I want to plot the block diagram, what I'm going to do is that I'm going to bring all terms, with the exception of the term with the highest degree of the polynomial, to one side. So here I bring a1 y dot and a0 y to the other side. So now what remains is an equation with u, y, and y dot on one side, and then on the other side I have y double dot. Now on my page, I mark a point on the page as y. I say, okay, this is a point that I call y of t, and I create or generate y dot and y double dot from that. How do I do that? Well, previous slide we studied, which 1 over s. So then you generate a 2y double dot by putting a 1 over a2 block in front of it, and then we generate all these pieces that we already have and add them up using a sum. Okay, so that was a symbolic way of explaining it. Before we go to case 2, let me show you an example. Okay, so I have an example. We are going to come back to this page because we have two examples here. One of them is case 1. There is no derivatives of the input in this equation. And then example 2 has derivatives of input on the right hand side. So it's case 2. We are going to come back to it. So right now we want to just work on case 1. Okay. How can I create or draw a block diagram of this differential equation? Well, first I bring this term to right hand side. So I'm going to write it as 3y double dot equals to negative 5y plus 6u. Now I mark a point on the page on my paper as y, and then by putting blocks, 1 over s blocks, I create y dot and y double dot. Okay, all I have achieved until now is that on my page I have y dot and y double dot shown. Now if somebody asks me to use a block somewhere on my page to create 3y double dot, what can I do? Well, I know where y double dot is. I want to create 3y double dot here. What should I do? Well, I want 3y double dot to be multiplied by something to give me y double dot. That is probably 1 over 3. So by putting a 1 over 3 block here, I have now 3 y double dot. Okay, so I created 3y double dot. That is supposed to be equal to negative 5y of t plus 6u of t. So this is supposed to be equal to negative 5y of t. I already have y on my page. And then I show another point on the map with u, and I create 6u of t, and then I add them up. So now I have 3y double dot is equal to 6u of t negative 5y, which is what I had. I could have terms with y dot in them. I simply just put another block here and then add them up in the summation point. So that's what I do in case 1. In case 2, I have derivatives of u. I can have u dot or u double dot here. So now the trick is to do this. I have to first find the transfer function. So I take the Laplace transform, write the transfer function here. Then I break the transfer function into 2 pieces, the numerator versus the denominator. And I introduce an intermediate variable. I show it with v. I say, okay, the denominator is now a new system. It's a system for itself. I call it a system with u as an input and v as an output. And then the numerator, I say, well, it's v as an input and y as an output. Okay, so I take the Laplace transform, I write the transfer function, break it into 2 pieces, the numerator versus the denominator, and then I introduce a new variable to be the output for this transfer function and the input for this transfer function. Now, I write down the differential equation for these 2 new systems. Okay, so now all I have done is that I had a differential equation with u dot, and u double dot, and I was not happy with that. I didn't know what to do with it. Broke it into 2 differential equations. There is no u dot or u double dot anymore. There's just u. But now I have a new variable which has which appears in my equations, and then I have derivatives of it too. And that's fine. Why is it fine? Because now I have the derivatives of it appear in both equations. So the trick is basically to break that differential equation into 2 differential equations. And now I want to draw the block diagram based on v. So what I do is that now I try to look at this. How can I plot the block diagram for this? Well, it's very much like case 1. I have u, I have v, v dot, v double dot. I bring these 2 terms to the right-hand side. I mark a point on the map as v, create v dot and v double dot from it, and then a2 v dot, v double dot, and then let's see, we had a0 v, a1 v dot, a2 v double dot. So this piece, this part here, would be the equation, the first equation. Now for the second equation, notice that I need to have y, and then again v dot, v double dot. I already have v dot and v double dot, so I can just mark a point here as y, then add them up, and that gives me the second piece. It's the second differential equation. So for this example, I encourage you to read it yourself. This is the example for case number 2.